In section 9.8, we are going to look at what's called higher order derivatives, particularly the second derivative. The derivative of the first derivative is the second derivative, and then the derivative of the second derivative is the third derivative. For notation, for second derivative, you can see the double prime symbols, or you might see the dy dx, but you put 2's on the d in the numerator and the x in the denominator. Third derivative is very similar, except it's 3 prime symbols and an exponent of 3. Anytime we go higher than a third derivative, we always use the numeral instead of prime symbols because it starts to get to be way too many prime symbols very quickly. For our first example, we want to find the second derivative. We just use the rules that we already know. So our first derivative will be 20x to the third plus 20x, which means that our second derivative will be 60x squared plus 20. On example 2, we want to find the third derivative. Our first derivative would be 20x to the third minus 36x squared. Our second derivative would be 60x squared minus 72x. And our third derivative would be 120x minus 72. One application of the second derivative is acceleration, which tells us if the object is speeding up or slowing down and the rate at which the object is speeding up or slowing down at a specific instant. On example 3, an astronaut standing on the surface of the moon throws a rock into the air. The height s, measured in feet, of the rock is given by this function s equals negative 27 over 10 times t squared plus 27t plus 6. We actually have 2 questions. It says find the velocity and acceleration of the rock at 2 seconds. Interpret your answers. So for velocity, remember we need the first derivative. So velocity is s prime. And if we drop that 2 times the 27 over 10, we will get negative 54 over 10t plus 27. We can simplify that to be negative 27 over 5 times t plus 27. We are supposed to find the velocity at 2 seconds. So the velocity at 2 seconds, if we put 2 into this, we will get negative 54 over 5 plus 27. If you work that, you will get 16.2, and our measurements are feet per second. Now, because our velocity was positive, when we interpret this, we know that the rock is moving, because it's positive, upward, whatever would be the positive direction, at 16.2 feet per second. Now we need to do acceleration at 2. Acceleration is the second derivative. So do the derivative of the first derivative, which will be negative 27 over 5. It's a constant. If we want to make this into a decimal, we can. We can think of it as negative 5.4. So what's happening here is that the acceleration is always 5.4, negative 5.4. What does it mean if your acceleration is negative? What that means is that the rock is slowing down at 5.4. Now our unit of measure still stays feet, but our unit of time, it's per second or per second squared. On example 4, we have another acceleration question. We have the position of a particle moving horizontally after t seconds is given by the function f of t equals 2t cubed minus 21t squared plus 60t. And then they give us this information about 0 less than or equal to t less than or equal to 6. That's telling you that this function only works for the times from 0 to 6 seconds. If it's beyond 6 seconds, the function would be different. The question says find and interpret the velocity and acceleration at 3 seconds. So, first of all, velocity will be the first derivative, which will be 6t squared minus 42t plus 60. Velocity at 3 would be 6 times 9 minus 42 times 3 plus 60. And if you work that all out, you get negative 12. We know that the time is being measured in seconds, but we don't know how our distance is being measured. So it's difficult to put a label on this one. What we do know, though, because it is negative 12, is that the particle is moving in the negative direction. Now, we don't know, it just says horizontally. We can assume that the negative direction is left, but we don't know that for sure. So that's why I just put negative direction. So now we need to find acceleration. And that is the second derivative. Doing the derivative of our first derivative will give us 12t minus 42. So if we find the acceleration at 3, we will do 12 times 3 minus 42. 36 minus 42 gives us negative 6. Again, we can't really put a label on here because we only know time. We don't know how we're measuring distance. So it's difficult to put a label on here. But the interpretation is that the particle is slowing down because the acceleration is negative. As most of you are business majors, it is important to understand the point of diminishing returns, which is the value or values at which an investment is not considered a good investment. You find this by finding when the second derivative equals 0. An example that deals with the point of diminishing returns is a local automobile dealer has found that advertising produces sales, but that too much advertising tends to turn off consumers, resulting in reduced sales. On the basis of past experience, the dealer expects that the number of vehicles sold during a month is related to the amount spent on advertising by the function v of x equals negative 0.1x cubed plus 2.2x squared plus 1.2x plus 15. And this is true for all values of x from 0 to 50. X is the amount spent on advertising in tens of thousands of dollars. We are to find the point of diminishing returns. Remember, by definition, the point of diminishing returns is where the second derivative is 0. So, first of all, finding the first derivative, you will get negative 0.3x squared plus 4.4x plus 1.2. Now find the second derivative. The second derivative will be negative 0.6x plus 4.4. To find the point of diminishing returns, we take that second derivative and set it equal to 0. So setting our second derivative equal to 0, to solve this, I'm going to add the negative 0.6 and get positive 0.6x equals 4.4, and then divide by 0.6, and we get x equals 7.3. Now remember what it says about x. It's 7.3 10,000s. So if you take that times 10,000, 73,000 would be where you have reached your point of diminishing returns. If you spend more than that, you will have turned off consumers. On our last example, we are going to be given figures, and there are 3 different graphs on these figures. One graph is the original function f, one graph is the derivative, and one graph is the second derivative. We are supposed to decide which one's which. If you think about these graphs, your original function is always the highest power. Your first derivative is 1 power down, your second derivative would be 2 powers down from the original. So if your original function is the highest power, then it's going to be the most complicated graph. So in this particular case, the most complicated graph is this one, which is the idea of a cubed function. It's been shifted in some way, so it's not just y equals x cubed, but it is a cubed function of some type. If you go down 1, then the derivative would be a square. Well, a squared function is a parabola, so f prime is the parabola, and the derivative of an x squared would be x to the first, which would be a line. So f double prime is the line. In looking at the second figure, the most complicated of the graphs is the parabola. So that has to be the original function. And it has to be some kind of ax squared plus bx plus c. We don't know what those numbers are, but because it's a parabola, it has to be an x squared. So think about that. The derivative of an x squared is going to be an x to the first. And if you have ax plus b, then you've got a line that's at a slant somehow. So the slanted line has to be the derivative. And then the second derivative has to be the horizontal line, because it would just be a. The derivative of ax is just going to be a. And if you have y equals a, you have a horizontal line.